In a much earlier section, we learned that we can represent a system of linear equations using a matrix. And I would do that simply by taking each of the coefficients of the variables. My variables here are x1 and x2. And I have constant terms on the right-hand side of my equation. And so I can take each of the coefficients of the variables on the left-hand sides of the equation and the constants on the right-hand side of the equation and sort of line them up, and that creates a matrix. And in fact, we said this was an augmented matrix. You can write the line or not write the line here because it represents a system of equations, right? Because the variable values are here and here, and the constant values, the right-hand side of the equation, the constant values are on the other side of the line. Now, the line is not strictly speaking necessary, but it helps us to see that this is this type of matrix. But it turns out it's actually also very useful to write a system of equations, or to be able to write a system of equations as what we call a matrix equation. And that is different from a matrix in that an equation has two sides. It has an equals sign in it. Here, let's write an algebraic equation. 5x plus 3 equals 10. All right, there's an equal sign. That's what makes it an equation and not an expression. And in order to solve for the variable, we need to perform various inverse operations to isolate that variable. So what we're going to do to solve this equation is to subtract 3 and then divide both sides by 5. That leaves the x by itself, and we have a value, in this case, because it's a linear equation, a single value, the only value of x that will work to satisfy this equation. Well, it turns out that we can do the same thing with matrices, but in order to do so, we need to learn how to write them as equations in their own right. What I'm going to do here is I'm going to make the observation that since all of the x1 coefficients are kind of lined up here, and in fact, I've done that over here too. These are all x1 coefficients. I'm going to write them kind of as a stack. I'm going to say 2, -3, and 7. And then I'm going to do the same thing with the x2 variables in the same way that I did them over here. Write them as a stack. -5, 8, and 4. And then the same thing with the constants. 6, -1, and 0. And so far, it doesn't look terribly different from the standard sort of augmented matrix that I've been working with. But here's where things get a little bit different. What I'm going to do now is notice that each of these constants is multiplied by x1. Well, x1 is a real number, so we can treat it like a scalar. And therefore, we can say that this column matrix, this 3 by 1 matrix, is being multiplied by x1. And to that, we're going to add, I've not left myself enough room here for an operation, but it's plus. We're going to add each of the coefficients multiplied by x2, recalling that x2 is really just a real number. It's a scalar. And then we can write our system of linear equations in this form. And this is what we call, the form that this is in now is what we call, sorry, I undid a draw there. Let me redraw that in. All right, now I'm going to ask you to trust me for a moment. I'm going to unmultiply two matrices together. The matrices that I'm going to unmultiply are the ones made of this column matrix and this column matrix. I'm going to call that matrix A. So I'll rewrite that here. 2, -3, 7, and -5, 8, 4. And once I've done this, I'll show you that it's legitimate that I can do this in the first place. I'm going to call that matrix A. And the next matrix I'm going to multiply, or I'm going to unmultiply from this sum up here, is the matrix consisting of x1 and x2. Remember, those are just real numbers. We just don't know what they are. So x1 and x2. And the result will still be 6, -1, and 0. And this is what we call a matrix equation. Okay, I won't expect you to be able to do this unmultiplying of matrices just yet, but I do want to convince you that what I've done is legitimate. So what I'm going to do now is multiply this matrix here, A, by this matrix of variables and show you that what it gives me is this same setup that I have up here. So this is a 3 by 2 matrix, and this is a 2 by 1 matrix. The middle numbers match, so that means I can do this multiplication. And what I'm going to get when I do that is negative 2 times x1 plus negative 5, so I'll write that as minus 5 times x2. And then I go to, having done row 1 with column 1, I'm going to go to, there is no column 2, right? So just go to row 2 with column 1 and so on. So my row 2 with column 1 is going to be negative 3 times x1 plus 8 times x2. Forgot my 1 there, plus 8 times x2. And for my third row times my column 1, I'm going to get 7 times x1 plus 4 times x2. And that's the same as the left-hand side of the system I have up here, from which I made this. It's not really a matrix equation yet in this form here. It's getting closer, but in that step, right? So that's how I got that step. This matches what I had on the left-hand side to start with. So this matrix multiplication that I did right here gives me this system, or gives me the left-hand side of the system, and that in turn gave me that. So these three things on the left-hand side are equivalent. And this line that I have down here, this matrix A times this matrix made up of variables equals this column matrix. This is what we call a matrix equation. And we have some sort of shorthand notation that we use. A is already labeled matrix A. I'm going to call this column matrix of variables a matrix X. And usually if you see this in print, it's a bold X. And sometimes it's a capital X. I can't write that here, but I'll write it on the next sort of step. And then this other matrix that we've got over here, this single column matrix, because it is also a matrix, we're going to give it a name too. And again, just sort of conventionally, we use a lowercase letter for that, and that's a letter B. So you might see something like this. Of course, I'm not doing this in print, so I'm kind of having to fudge things a little bit here. AX equals B. It's a nice bold B. You might see AX equals B. And when it's handwritten, you very likely see just AX equals B. And the way to know that this is a matrix of variables is by the context, right? First of all, you're unlikely to see an equation like this completely in isolation. You'll know the type of problem that you're working on, and you'll know the sort of scenario that you're coming from. And then this A here, once you know the context is linear algebra, it's very likely that this is a matrix. So it makes sense that this is a variable matrix as well. So hopefully that has convinced you that this matrix multiplication that I wrote here is legitimate to have come from the step above. The matrices involved can be of any size, as long as they're appropriately sized to be able to do this multiplication. So this matrix might be a 12 by 17 matrix, and this would be then a 17 by 1 matrix, and this would be a 12 by 1 matrix. We would still use the notation though, AX equals B for that matrix equation, even though the sizes of the matrices were very different. Instead of being a 3 by 2, if this was a 12 by 17, but it was called A, it would still be represented by A. This would then be a 17 by 1, and that would still be represented by X. This would be a 12 by 1, and that would still be represented by B.